Welcome to this explainer. I'm absolutely thrilled you're joining us today. We're diving into the incredibly, perfectly balanced world of triangles. But not just any triangles, right? We're zoning in on the geometry of isosceles and equilateral triangles. These foundational shapes, they're essentially the building blocks for so much of the math and engineering we rely on every single day. So, let's visualize the exact logic that makes these shapes so special. Ready? Let's dive in. Okay, here's our quick roadmap for today. We'll be hitting 5 key areas. First, classifying types of triangles. Second, the Isosceles Triangle theorem. Third, equilateral triangle properties. Fourth, the axis of symmetry. And finally, number 5, bringing it all together with medians, bisectors, and perpendiculars. All right, section 1, classifying types of triangles. Let's just set a quick baseline for how we categorize these shapes.
So triangles are classified by their side lengths into 3 distinct types, which you can easily spot by looking at the little tick marks on their sides. A scalene triangle, 0 matching marks. That means all 3 sides are totally different lengths. An isosceles triangle has 2 congruent, or perfectly equal sides. And then there's the equilateral triangle, where all 3 sides match up perfectly. Today, we're keeping our focus squarely on the isosceles and the equilateral.
Moving right along to section 2, the Isosceles Triangle theorem. Let's get into the core rules and internal logic here. Okay, here is an absolutely crucial rule known as Theorem 5-1. The base angles of an isosceles triangle are always congruent. What does that actually mean for us in practice? Well, if a triangle has 2 equal sides, which we call the legs, the angles sitting directly opposite them at the base simply must be equal to. The sides literally dictate the angles. It's really one of nature's great structural secrets. Now, what's super fascinating about this relationship is the specific nature of those base angles. You know that a triangle's internal angles always add up to exactly 180 degrees, right? Well, because our 2 base angles are identical twins, they absolutely always have to be acute, meaning they're less than 90 degrees. If they were 90 or more, well, you just run out of degrees for that top angle. But that top angle, the vertex angle, it has total freedom. It can be a sharp acute angle, a perfect 90-degree right angle, or a wide leaning obtuse angle. We've just seen that equal sides create equal angles. But, in mathematics, we always want to test the boundaries of our logic. So, what if we reverse the rules? What happens if we look at the angles first? Well, it turns out the relationship is a two-way street. The original isosceles theorem tells us that sides dictate angles, but the converse of the theorem proves the exact opposite is true too. If you happen to notice 2 angles are perfectly congruent, you can confidently declare that the sides opposite them are perfectly equal in length as well. That brings us to section 3, equilateral triangle properties. Let's take this idea of perfect balance and push it to its absolute extreme. I absolutely love sharing this next concept because it's like a brilliant mathematical shortcut. Equilateral triangles are basically the overachievers of the geometry world. Everything has to be flawless. So if you know a triangle is isosceles, meaning 2 sides are equal, and you find out that just one of its angles is 60 degrees, boom. The entire shape instantly upgrades to equilateral status. Just think about the logic for a second. If the vertex is 60, the remaining 120 degrees have to split evenly into 60 and 60 at the base. Or if a base angle is 60, its twin is 60, leaving exactly 60 for the top. It's this inescapable, beautifully perfect loop. And just like the isosceles theorem, the equilateral triangle has its own perfect two-way loop. If a triangle is equilateral with 3 equal sides, it's automatically equiangular, meaning it has 3 60-degree angles. Conversely, 3 identical angles guarantee 3 identical sides. Equilateral and equiangular are literally just 2 sides of the exact same geometric coin. All right, section 4, the axis of symmetry. We've established the outer perimeter, so now let's slice these shapes right down the middle to see their internal mechanics. Let's clearly define our core concept first. An axis of symmetry of a line segment is a straight line that does 2 very specific things. First, it's perpendicular to the segment, meaning it crosses at a perfect 90-degree angle. Second, it passes exactly through the segment's midpoint, slicing it into 2 flawless halves. You can kind of think of this as a strict geometric checklist. To prove a line is the true axis of symmetry for a base segment, you just check 2 things. Step 1, is it perpendicular? Yes. Step 2, Does it bisect the line exactly in half? Yes. Well then, congratulations. You've just found your axis of symmetry. It's a perfect mirror line. Now, because that mirror line perfectly splits the base, any single point you pick anywhere along that vertical axis will be the exact same distance to the endpoints or terminals of the baseline. You're essentially creating an isosceles triangle out of thin air just by picking a random point on that axis. It forms this perfectly balanced tent right over the base. And true to form, mathematics gives us another two-way street here. If you have a floating point in space that happens to be perfectly balanced or equidistant between the two ends of a line segment, that point absolutely must sit somewhere on that invisible axis of symmetry. The balance basically guarantees its placement. Okay, we are in the home stretch. Section 5, medians, bisectors, and perpendiculars. Let's bring this all together. Consider this your ultimate geometry cheat sheet. When you draw a line straight down from the top vertex of an isosceles triangle, 3 magical things can happen. 1, it can act as a median, cutting the base in half. 2, it can act as a bisector, cutting the top angle in half. Or 3, it can be a perpendicular line, hitting the base at exactly 90 degrees. The incredible secret here? If it does just one of these things, the rules of symmetry guarantee it automatically does the other 2 as well. The axis of symmetry basically locks all 3 of these properties together in this unbreakable harmony. If you draw a median that cuts the bottom line in half, you get the 90-degree angle and the perfectly split top angle for free. If you only split the top angle in half, you get the split base and the 90-degree angle for free. One property always guarantees the other 2. It's literally a built-in structural cheat code for geometry. So we've unpacked a ton of logic today, and it all flows from the incredibly simple idea of equal sides and equal angles. But I want to leave you with a thought as we wrap up this explainer. As you go about your week, take a look at the architecture around you. Look at the steel trusses of the bridges you drive over, or the scaffolding on a big construction site. Could the rigid symmetry, the perfect balance, and those unbending rules of the isosceles and equilateral triangles we just explored be the very secret holding up our entire modern world? Keep your eyes open and keep learning. Thank you so much for joining me today.